Hello, friends. Here's a compilation of some previously recorded lectures on the topic of conservation of momentum and center of mass. They were taken some years ago, so not as much gray in the beard. Also, the way that the course was structured is that we start at the very beginning, like the very first class would always be center of mass, algebraic, and then we would do something hands-on just to start the year with something hands-on. And so if things look kind of a little out of order, it's because I took that thing from the first unit, the very first lecture, and I stitched it into this one. But we start with conservation of momentum, momentum, conservation of momentum, and then get into uh, center of mass. And I tell my students that really, um, if you can try to look at it this way, conservation of momentum, center of mass, and Newton's third law are really all the same thing. They're all just different ways of saying the same kind of thing. It's this tight unity that they have. Try to see it that way might be a helpful concept. So hope you enjoy these videos. The links to the lecture notes are down in the description, so check that out. And don't forget to like and subscribe and share. Now we're going to start with momentum. We're starting with section 9.4. And so momentum is P equals mv. V is a vector, P is a vector. You know that for a system of particles, it works the same. This is for one object, but if you have a bunch of objects, it works the same way. And sometimes it's capital P, M, V, time, and if you add up all the M and V of the whole system of particles, then it works the same way. You can talk about the momentum of any system. As long as you define this is the system I'm talking about, it can include as many objects as you want. And then the rules for momentum work. We can also relate it to the net force, right? Let's think about it this way, right? What is mv? mv is dx dt, right? All right, so let's look at force. F equals ma, right? And what is a? M dv dt. But if we multiply dv by m, then what we end up with is d mv dt. So the force is actually related to the rate of change, rate of change of the momentum. Right? So force, let's put arrows on our vectors here. The force of the net force on an object is equal to the derivative of the momentum. Okay, and actually this is how, as long as m is constant, by the way, this is actually how Newton wrote his second law, that the net force is equal to the time rate of change of the momentum. He didn't say F equals ma, he said F equals dp dt. Just historical note there. And the same is true for a system of particles, right? F net is going to be equal to d capital P dt. So then if we have a graphical analysis of momentum, if the momentum graph looks like this, right, P and T, the force graph then is going to look somewhat, so this is positive slope, this is the place where the slope is 0, so it'll be like that. And it's negative the whole time, and then eventually we have negative, so this is the place where it reaches the most negative and then goes to 0. So it's going to look something like this. Right? This is what the force time graph would look like given this momentum time graph. Right? Conservation of linear momentum, again, if the net external force acting on a system is 0, then the total linear momentum remains the same. All right, you're familiar with this, and this is true for each of the vectors, right? Horizontally, vertically, you can look at it all these different ways. Just like a projectile, the net force vertically is gravity, and so you're going to see change in momentum vertically because there is an external force. Horizontally, there's none. So we can think about even something like projectile motion in terms of conservation of momentum. All right, so different types of collisions. You've got elastic, completely inelastic, partially inelastic. You're familiar with all this stuff, right? Momentum and kinetic energy in collisions. Momentum is always conserved. No matter what the collision is, elastic, inelastic, the total momentum is always conserved.
The total kinetic energy may not be conserved, though. That's the difference between elastic and inelastic and that kind of thing. Again, you know this. If the kinetic energy is conserved, it's called elastic. If it's not conserved, then it's inelastic, which could be totally inelastic, where the things stick together, or partially inelastic, where they don't stick together, they do bounce off, but some kinetic energy is still lost into some other form of energy, usually heat or something like that. And you have some diagrams here, all just illustrating conservation of linear momentum. Two ice skaters coming together. Collisions, again, can be elastic, completely inelastic, partially inelastic. Impulse. I don't know what letter you've used in the past for impulse, but in this class, we're going to be using J. And J is not terribly uncommon to see. It's just sometimes not introduced in introductory physics or first-year physics because it's a little confusing. So J is interesting. Impulse is interesting, and it can be really confusing because it has its own name. Impulse. This is one of the few places where we say the change in something has its own name. Impulse, all it is change in momentum. That's it. Anytime you hear impulse, you think impulse, you see it, J, just think change in momentum. In fact, it might be helpful that anytime you see it, just substitute delta P. Substitute that in there to help you think about it. Now, since this is the change momentum, and we also know that J is going to be equal to, from time initial to time final, the integral of force with respect to time. Right? Because force is the derivative of this, so the antiderivative of this will give us the change in this, right? And so let's look at this in terms of units as well. We want to keep units in mind here. According to this, J is going to have units of Newton seconds. Right? How does that work out? A Newton is a kilogram meter per second squared, again, times seconds. So this is a kilogram meter per second. Mass times velocity. Right? So it works. So again, if you forget the unit, if you forget this, like, oh, the impulse, is that the derivative or the integral of the force? Just think to yourself, this, what are the units? Units on force, newtons. So if I multiply that by seconds, multiplying units is like, that indicates taking the integral. Taking the derivative is when you're dividing. So if you had this and you wanted to get to force, you're like, okay, well then this divided by seconds is going to give me the right units for force. Dividing is like taking the derivative. Okay. And so then we have some graphical representations here of the impulse, right? The impulse is equal to the area under the curve, and if you can estimate it with a rectangle if you have to. This comes from Newton's second law. Again, like we said, I took it down already. Newton's second law is, all right, other important information there. All right, so now we have an example. Let's take a look at it. So in this problem, the way I wrote it was that VI is 30 meters per second and VF is negative 37 meters per second. I wrote that because we find out here that it's struck and then it's moving in the opposite direction. So I'm just going to make the initial direction positive and the final direction negative. First question is asking, what is the impulse of the bat on the ball? So let me, just one more thing here. So we're saying initially it's moving this way, 30 meters per second, and then afterwards it's moving that way at 37 meters per second. Right? It's coming this way, it hits it with the bat, and then it's moving in the negative direction that way. So part A, what is the impulse? Well, impulse is delta P. Delta P is going to be m, same mass, VF minus VI. All right, change in momentum. I just factored out the mass there. Okay, skipped a step algebraically. And so when you plug in the numbers, this is going to be the 1.5 or the 0.159. This is negative 37, and this is 30, right? So negative 37 minus 30. And when you do all the calculations, you end up with negative 10.65 Newton seconds. We can put it in terms of Newton seconds. That's okay. All right? That means the net force on it was in that direction, right? Think through what that means. And we would expect that because the change in the velocity was in that direction. All right, so part B now asks us what is the average force of the bat on the ball. Again, we're looking for average force here because in reality, a bat hitting the ball, it's a constantly varying force. It starts off small and then a lot and then a little over a very small period of time. So we're just asking for the average force, and that saves us from having to use calculus. So J equals Ft. We know J from this, and we know the time was just given to us. So the force is the impulse divided by the time, so negative 10.65 Newton seconds over 1 millisecond, so 1 times 10 to the negative third seconds. Well, that gives us negative 10,650 newtons. That's good. You can see the units, the seconds cancel out, and we're left with that. Okay, in example 2, we're given this function of the force. We're saying given this function of the force, we want to know what is the impulse on the body from 0 to 3 seconds. If we have the force function, we don't know what the initial and final momenta are unless they're given to us. So what we can find here is just the change in momentum. But what is the change in momentum? It's the impulse. All right. And here we're using calculus. And so the impulse, as we saw before, is the time integral of the force function. And so this is going to be from, let's just say Ti to Tf of 2t squared plus 3t dt. All right, so this is going to be 2 over 3 t cubed plus 3 over 2 t squared from 0 to 3 seconds is what the time that's given to us. So we plug these numbers in, and when I want to go through, take your time that way, but when you plug the numbers in, you should get about 31.5 Newton seconds. Okay. Example 3 is similar, except that here we're given the momentum function. And here we want to know the net force on the body at 3 seconds. First thing we do, take the derivative, and we get the force function as a function of time, and then we just plug in 3. So when we take the derivative of this, F is dp dt. So the derivative of this is going to be 4t plus 3. Okay, so then the force at 3 seconds, we just plug 3 into this, right, and we should get 15 newtons. So this is example 3. Okay. The first example 3. I guess we have 2 example 3s. So again, impulse linear momentum theorem is that the change in momentum is equal to the momentum, or the impulse. And in 3 dimensions, so we can write this down, this is true that the change in the momentum in the x direction is equal to the impulse in the x direction, the y direction, and the z direction. All right. This one is just a repeat before. So now the second example 3 with a 1,000-kilogram car. Okay, so here we've got 2 cars moving along the highway, both moving east, so they're both positive velocity here. This one is moving slower than this one. It gets rear-ended. And the 2 stick together. It's perfectly inelastic. So now we want to find the final velocity of the wreckage. So this is going to look like this. P1 plus P2 equals P3. And it's all in the same direction, so I'm not going to write the vector signs. We can deal just with magnitudes now. And so this is mass times velocity plus mass, so 1,000, times velocity equals, and then the final mass, the total resulting mass, this should be 4,000 kilograms times VF. And that final velocity is going to be about 27.5 meters per second. All right. Simple problem, something you could have done last year for sure. So now in this problem, we start off knowing the initial velocities of two balls, and then we want to know the final velocities of these two. We know that it's elastic, so that means that the kinetic energy is conserved and the momentum is conserved, but we don't know either of the final velocities. Ultimately, the question asks for what is the final velocity of the 1 kilogram ball. So that's what we're going to try to find. But, so because this is elastic, we can write two equations. We can write the momentum equation, right? M1 V1I, which is what I did here, the initial velocity of this ball, plus 0, right, because the momentum of this one is 0 to start with, equals M1 V1F plus M2 V2F. All right. And then these are the two things I don't know. All right. And then, let's see, for energy, this is the total kinetic energy to start with, and that's going to equal 1/2 M1 V1F squared plus 1/2 M2 V2F squared. Okay, so let's plug in some of the numbers because we're dealing with simple numbers like 1 and 4 and 10, so we can put in some of these things. This turns out to be 40. This is going to be 4. I'm just going to call this VF now because I'm plugging in the numbers for V1I. Or sorry, so I'm going to call this V1 plus, this is just now V2. That's 1 there. Now I'll plug in here, so this is going to be 1/2 of 4 times 100, so 200 is 2V1 squared plus 0.5 V2 squared. So I've got this, and I've got this. I've got these two equations. And so what I'm going to do is I'm going to solve for V2. So here V2 equals 40 minus 4V1. Now I'm going to plug this into here. So I'm going to have 200 equals 2V1 squared plus 0.5 40 minus 4V1 squared. Right? And so this is getting pretty ugly. Where did that 0.5 go? Oh, I see what I did. Okay, so to get rid of the 0.5, we're just going to say 400 equals 4V1 squared plus 40 minus 4V1 squared. So now I have one unknown and one equation here. And when you solve this, turn it into a quadratic and set it equal to 0, you get 0 equals 20 V1 squared plus negative 320 V1 plus 1200. You can factor out 20, believe it or not. And so you get V1 20 times V1 squared minus 16 V1 plus 60. This, you can factor this, right? Because 10 and 6, negative 10, negative 6. So 0 equals 20 times V1 minus 10, V1 minus 6. And so then if V1 is equal to 10, so if I plug this in here, if V1 is equal to 10, then V2 has to be equal to 0. And that doesn't make any sense, because if these two collide, what I have there is basically this one just continuing straight through, and this ball not even moving now, because this still has its same initial velocity. But if v1 is 6, then v2 is 16 meters per second, and that looks better. Now that was a lot of work, having to go through and solve two equations and use quadratic formula, and that's why in the next lesson I'm going to show you a shortcut. There's a magic formula for dealing with problems like this: elastic collisions, two bodies, and not knowing either of the final velocities. So we're on 9.8 to 9.11. First example, derive a general expression for the initial velocity of a ballistic pendulum as a function of height. So first of all, a ballistic pendulum, what is that? Typically it's a block of something that's hanging, so that's the pendulum part. The ballistic part is that we have a bullet or a rock or a ball or something that hits this block and then sends it swinging. That's a ballistic pendulum. And so in this case, we want to know the initial velocity of this object, whatever this object is. We want to find what this is as a function of the height that it reaches over here. Right? And so we've got two things. We've got little m and big M here. This is initial condition. The final is that this smaller thing has embedded itself into the bigger thing, and it has reached, they together have reached some height h. The mass of this thing now is m plus m, little m plus big M. That's what we've got. Okay, and so what do we have here? It's two things. We've got a conservation of momentum problem, and we have a conservation of energy problem. Conservation of momentum with the collision. Now it has some initial velocity, and conservation of energy reaching this height, right? How much kinetic energy does it have being transferred to gravitational potential energy with that height? So we've got mvi, so we're going to call this vi, equals m plus big M vf. All right, that's what we'll call that. And then we'll go over here and write our conservation of energy equation. 1/2 little m plus big M vf squared equals 2 little m plus big M gh. Not 2 m. I don't know why I wrote that. Little m plus big M gh. Right. So now we want to solve for this. The m's cancel out, and so vf is equal to the square root of 2gh. Right. So this now we can plug into here, and so we have m vi equals m plus big M times the square root of 2gh. So this looks good. We want this as a function of this. So now all we have to do is divide by little m. So vi is m plus big M times the square root of gh over little m. So now we have the initial velocity as a function of the height. So we know we have some ballistic pendulum, we know the masses, and we know how high it gets at the end. From that now we can calculate what the initial velocity is. Okay, so then we have this thing about a series of collisions, a steady stream of particles, and all these particles have the same momentum, right, mv, colliding with a target in a fixed place. You can see the next example, something like this would be like a machine gun, right? A lot of bullets happening one after another, hitting some object. And so what we can do here is think of it this way. The average force vector, right, is going to be negative, so the negative of the change in momentum, n times delta p, because delta p would be the change in momentum for each individual particle, right? So we're multiplying that by the number of particles and then dividing by delta t. All right. Or we can say that this is negative n times m times delta v over delta t. But the number of masses hitting, n times the number of masses is kind of like the change in mass times the change in velocity over the change in time. So all different ways of expressing the same thing there, right? And so we have an example with this. Superman experiences a spray of 0.1 kilogram bullets striking his body at 1,000 bullets per minute. So that would be the N. Or 1,000 bullets per minute. So we need to find how many that is per second. At an initial velocity of 500 meters per second. So calculate the force on Superman if the bullet stops, and then if they ricochet off of Superman. All right. So I'm going to set it up this way. Or rather, I think this would be better. N m delta v. So I've got n over delta t because that is, I know I've got 1,000 bullets per 60 seconds. Right. The mass of each one is 0.1 kilograms. And the change in velocity in this case is negative 500 meters per second. Right. So this is going to be 833 newtons. That's it. In the second case, where they ricochet, the only difference here is that now, instead of them stopping, going from 500 to 0, they're going from 500 to 300, but in the opposite direction. So the total change in velocity, delta v, is 800 instead. And so this is all set up the same way, but for part B now, it's going to be negative 1,000 over 60 times 0.1 kilogram times negative 800 meters per second. And that result is going to be 1,333 newtons. Okay. Now, the next thing is these general equations for one-dimensional elastic collisions. In the last lecture, we had this problem where we knew the initial velocities of two objects, there was an elastic collision, and then we didn't know either of the final velocities. And we had to use both momentum and energy to solve that, because we needed two different equations that had velocity in it, two equations, two unknowns, and we had to do all this solving. It was a mess. Here is a derivation for a formula that'll help you out in any of these situations. If you know that there is an elastic collision and you know the initial velocities and you can find both of the final velocities using this formula. Okay, and you can follow it, go step by step through the whole thing using conservation of momentum, conservation of kinetic energy. It's basically doing what we did before, but with all the variables. There's one key thing in here, right? In the second page, there is this equation, V1I plus V1F equals V2F plus V2I. Right. This is one really nice, simple equation that you can use sometimes. All right, so I would say this is one that you want to memorize. Also notice here what this is. It's V1I minus V2I equals V2F minus V1F. So the difference of the velocities have the same magnitude. So thinking about it in this way is helpful also if you want to do that. So very, very helpful little equation. And then the resulting equation at the end also, that's the one you can actually solve it and it'll give you V1F when you apply it that way. Okay. So some other general equations for elastic collisions. V1F to find V2F, that's that same equation that we derived from before. So now we want to look at some special cases. What if M1 is equal to M2? So this is like the case of a billiard ball, right? Where they hit. In this case, they exchange velocities. So you could say this, that V1F equals V2I and V2F equals V1I. They exchange velocities. B. What if V2I equals 0? So initially, the second object is not moving. Then In that case, one of the terms disappears. So you can see that V1F is M1, M2 over M1 plus M2 V1I, and V2F is 2M1 over M2 plus M1 V1I. C. What if they are equal in mass, though? Well, if they're equal in mass, and one of them starts off with velocity 0, V2 starts off with velocity 0, if they're equal in mass, see what happens here. Oh, sorry, this should be a minus on the top. M1 minus M2. Okay, so now it makes more sense. This ends up being 0. So V1F equals 0, and V2F, if it's the same mass and you have 2m and 2m also on the bottom here, and so this is 1, so V2F equals just V1I. So again, they just they switch velocities just like here, except that in this case, V1I or V2I was 0. Right. D. What if M1 is much, much, much bigger than M2 and V2I is 0? So imagine this. We've got some gigantic object rolling along and hitting some really tiny object. Like, let's say it's really big, like a really heavy bowling ball hitting a ping pong ball. What's going to happen in that case? Well, what's going to happen is this thing is so big compared to this that this one, the velocity is hardly going to change. So V1F is equal to V1I. Right. This one, the velocity is really not going to change. But for the smaller object, if M2 is really tiny compared to M1, look at V2F. You've got 2 times M1 over M2 really doesn't matter because it's so small. So it's like 2M1 over M1. This is saying 2 times V1I. So in that case then, V2F is going to be like 2 times the initial velocity of the big object, 2 V1I. It's so big, this one hardly moves at all, and then this one bounces off at twice the velocity of this. Last one, what if, oh sorry, that was E, actually. So this is situation E. Apologize for that. And then what about situation F? Let me go up here. Sorry, we need to go back to situation D. So if you've got a really tiny object bouncing into some really big object, in that case, this thing, if it's so big, it's not going to change. It's not going to move. It's not going to start moving. This is just going to bounce right back off. Right? An obvious example of this is dropping a bouncy ball. And a bouncy ball, you drop it. The bouncy ball, the mass is so small compared to that of the Earth that the Earth's velocity doesn't change at all, as far as we can notice. But the bouncy ball just bounces back up, but in the opposite direction with the same speed. Right? Assuming perfectly elastic collision. And so as a result, V1F is equal to the negative of V1I. And V2F is still 0 because it was initially 0. Right. And we do have situation F. This is an addition. In addition to what you have here. Right. Another one to add. This question is, when V2 is 0, V2I is 0, what percentage of energy is transferred from M1 to M2? So V2I equals 0. What percentage of energy is transferred from M1 to M2? All right, so really what we're looking at here is, K1I is K1F plus K2F. Right, it's totally elastic. V2I is 0, so there's no elastic potential, or there's no kinetic energy for the second object in the beginning. Right, and what we're asking here is, what is K2F to K1I? So what percentage, what ratio of this is now in this? So the ratio of K2F to K1I. All right, so let's take a look. So K2F is going to look like this. 1/2 m2, and then this final velocity, we can plug in what we had before. m1 over m1 plus m2 times, v1I squared over 1/2 m1 v1I squared. So some things cancel out. This cancels out with this. One of these guys is going to cancel out with one of these guys, and this is going to cancel out with this. And so I'm going to be left here with 4 m2 m1. All right, one of these m1s from here cancels out with this one, over m1 plus m2 squared. So this is the percentage of energy that's transferred to the second object, if it's a perfectly elastic collision. If m1 is equal to m2, then what we have, let's see, if m1 equals m2, so then this is 4m squared over, this is 2m, but it's squared, right? So 4m squared equal 1. That means 100% of the energy is transferred. And that's what we said before. That's the billiard ball example where they're the same mass. One of them is at rest, the other one's moving, and then they exchange velocities. So the second one is moving afterwards and the first one stops. 100% of the kinetic energy is released to that second one. So part F, question F is what percentage? It's this. And then I guess we could say, we keep going in the alphabet. The next one would be if they're equal to each other, then 100% of the energy is transferred to the next one. Right? And now this example, glancing blows. Okay, glancing elastic collision of identical masses. This is important. Every time there's a glancing blow, every time there's a glancing collision, right? So it results in two dimensions, things going off at angles. The angle between the final momentum vectors is 90 degrees. So let me illustrate this in this problem. We've got a gas molecule, 300 meters per second, collides elastically with another molecule of identical mass. That's nice. And after the collision, the first molecule moves off at an angle of negative 30 degrees from its initial direction. Find the speed of each molecule after the collision and the direction of the target molecule. So here's what we have. Molecule 1 is moving this way at 300 meters per second, and here's molecule 2. They're the same mass, so I'm not drawing this to scale. And what we have here, once they collide, M1 is now moving this way, and this is 30 degrees. That means that this, M2, this has to be 60 degrees, because the angle between these, where they're going off, is always 90 degrees. Okay, always. That's going to be key later on. Okay, you're going to see that. Again, it's going to come up. Glancing blows always 90 degrees. I'm saying that because I've said it before and then people forget later on. Don't forget, glancing blows, elastic collisions, 90 degrees. That's the angle between these resulting momentum vectors. Okay, velocity vectors. Okay, so these are actually really nice and easy to solve then too. One of the temptations here is to break these up into components. Find, what's the horizontal component? What are the vertical components? The vertical components have to be the same, right? What do the vertical components have to add up to? 0, because what is the initial momentum, pi, in the j direction is 0, right? So we would say, the vertical component has to be the same as this one, but then the two horizontal components have to add up to 300 kilogram meters per second, whatever times the mass, so we can calculate that. But here's the thing. We've got this momentum. These two momenta have to add up to this one, even as vectors. And so I'm going to call this P1I equals P1F plus P2F. And we can use vector arithmetic then. We look, oh, we can draw this out as a triangle, right? Here, this one is here. This is the m times 300 meters per second. That's got to be equal to this m1 v1f plus m2 v2f. And we can write this out even more, right? M v1i equals m v1f plus m v2f. Watch, the m's cancel out. And so I know these have to be related to each other by the Pythagorean theorem, but I also know that this is 30 degrees. So obviously not drawn to scale here. This should be like the other way. This. Wow. So you can see why I'm not an artist. This is not going well. This is 60 degrees here. So then if this is 300, that means this has to be 150, right? And this is 150 root 3. Sorry. Okay. And so the final velocities are v1f is 150 root 3 meters per second, and v2f is 150 meters per second. Right. Again, nice thing about vectors, if you've got 90-degree angles and you've got some vector arithmetic where the vectors add up in this way, then you can use right triangles. Oftentimes it's going to be a Pythagorean triple or one of your unit circle triangles, and that makes it nice and easy. Okay, so now we're on to onto section 9.12, and we're going to be talking here about changing distribution of mass. The key idea here, what are we talking about? The application, it's rockets. Okay, so think of like recoil problems, right? If you're holding on to something heavy and you throw it, you get pushed back. But if you're think of like a fire extinguisher on rollerblades, right? There you have a constant stream of particles that are being let out, and then you go in the other direction. That's what happens when you hold a balloon, you blow up a balloon and you let it go, and it flies through the air. Why is it doing that? Conservation of momentum. A lot of mass, it's a constant stream of mass going out. Why does the balloon go all over the place? Because as the little end of the balloon is flapping around, it changes the direction of the force as some of those particles are leaving the balloon. Okay, and so rockets are systems of varying distribution of mass. The mass is changing. Okay, and since the mass is changing, we're not using VIFTAD. The acceleration will probably not be constant. Not because the force is necessarily changing on the particles on each other, but because the mass is changing, and so the acceleration will be changing. And so we have this equation, relative velocity. The velocity of the rocket with respect to the Earth is equal to the velocity of the rocket with respect to the products. Products is the stuff that's coming out of the rocket, plus the velocity of the products with respect to the Earth. All right, so let's take a look at some of these equations. These are going to be some just sort of very specific equations that we use just for rockets, and it's the only place we apply them. We've got a few different things here, so we've got to be really careful about our letters that we use in our equations so you know what's what. Capital M is the mass of the rocket, and that is changing over time. Okay, V is the speed of the rocket relative to the reference frame, like Earth. dV is the change in the velocity of the rocket, because it is accelerating. dm is the change in the mass of the rocket. vrel is the velocity of the rocket with respect to the exhaust products. Okay, and then also, by the same token, the velocity of the exhaust products with respect to the rocket. U is the velocity of the exhaust products with respect to the reference frame, which is Earth. R is the rate at which fuel is consumed, and R is negative dm dt, right? Because it's losing mass over time. So here is a derivation. You can look through it if you want. It's based on conservation of momentum, but what we have is this changing mass distribution. And what we end up with at the bottom is this equation T. T is the thrust, by the way. 3 is R V rel equals MA. All right, actually capital M A. All right, that is our first rocket equation. Our next one leads to the second rocket equation. Again, going through the derivation, you can see that we're having to use calculus with, in this case, the changing mass and the changing velocity. And in the end, we end up with delta V is V rel. Remember, that's the relative velocity between the exhaust products and the rocket itself. Natural log of the initial mass of the rocket over the final mass of the rocket. Okay. And then the thrust or the recoil force, that's this. So actually the first and third equations are the same. Okay. And so, to summarize, here's your first rocket equation. And this, we can look at this and think of it as dm dt times v rel, right? Equals ma. Well, this is also equal to m times a is dv dt. Right. And if you follow this through and you add up like over a period of time, so you know your initial and final mass, then you can actually get back to this equation, which is what is done in the derivation. So let's move on to the examples and take a look. The engines of a first one, engines of a spacecraft provide a total thrust of 10 meganewtons. If the exhaust speed is 2.5 kilometers per second, at what rate is fuel being consumed? All right. So let's write out our quantities. Right. A lot of these problems are going to feel like plug and chug. So here we've got T, V rel, and we are looking for the rate at which fuel is being consumed. So what equation are we going to use? And we're going to use this one. Right. So R, solving this equation right here, T equals R. R is T over V rel. So this is going to be 1 times 10 to the 6th over 2.5 times 10 to the 3rd. We end up with 4 times 10 squared kilograms per second. Let's do a unit check on this, make sure it works. Thrust is newtons, so it's kilograms meters per second squared. And then V rel is meters per second. So this is kilograms meters per second squared, seconds per meter. So these cancel out, and we're left with just kilograms per second. So the equation works in terms of the units, and that's a good thing. Okay, so the first question asks for the thrust, right? So T equals the equation we had before, R times V rel. So here's R, and V rel is 1800 meters per second. So this is going to be 3.6 times 10 to the 3rd newtons. Simple enough. B asks for the acceleration at the beginning of the burn, so T equals ma, right? Thrust is a force. And we know the mass. This is only true at the beginning because the mass is what it is at the beginning and then it's changing after that. So that means the acceleration is changing. So the instantaneous acceleration at first is going to be the thrust over the initial mass. And that is 3.6 times 10 to the third newtons over, what do we have, 800 kilograms. So that comes out to about 4.5 meters per second. Next thing is the mass remaining after the burn. Okay. We know the rate. If we do the rate times the time, that'll tell us the change in mass, how much mass has been lost. So this is going to be 2 kilograms per second times 60 seconds. All right, it's burn first. So we lose 120 kilograms. So we start off with 800, we lose 120, and so we end up with 680 kilograms. And then part D, we want to know the change in velocity. So now we're using this natural log equation. So delta V equals V rel natural log mi over mf. V rel we said was, different problem over here, 1,800 meters per second. And then the initial mass is what we had before, 800 kilograms. And then we're ending with 680 kilograms. Calculate that, you get about 293 meters per second. Okay. So for 3, here are our quantities. And just think about these for a minute. 200 kilograms per second, that's a lot of mass to be losing every second. You know, like I have a mass of probably about 80 kilograms, so, you know, 2.5 of me every second. And then the stuff is coming out, the exhaust is coming out at 2,000 meters per second, so pretty fast. One way to get yourself going in another direction, you know, to like a big recoil, is either to have a large mass moving in one direction slowly, or have a lot of mass moving over a period of time, but moving very fast. Right? The faster that exhaust, the bigger the recoil is going to be. Right? So if we're looking for the thrust, again, like I said, this is a lot of plug and chug. That's what it feels like. R times V rel. So this is 200 kilograms per second. 2 times 10 to the third meters per second. We end up with 4 times 10 to the fifth newtons. Okay, and then what we're looking for is the change in the rocket's velocity when all the fuel is spent. All the fuel means 80% of this. And so 80%, or rather 20% of this is 4,000 kilograms. That's what's left after the other 16,000 has been spent. All right, so this is my final mass. And so delta V is V rel natural log mi over mf. V rel, 2 times 10 to the third meters per second. Natural log of the initial mass, which is 20,000, over the final mass, which is just the 4,000 kilogram payload. Right. You should end up with 3,218 meters per second. 4. In example 4, we're using the methodology of rocket problems, right? This constant stream of particles, exhaust kind of thing, but to another problem. So here we've got 2 long barges, and they're moving in the same direction in still water, one at 2.78 meters per second, the other at twice that speed. Okay, so while the faster barge is passing the slower barge, coal is shoveled from the slower to the faster at a rate of 1,000 kilograms per minute. how much additional force must be applied to the driving engines to the faster barge so that it can maintain its speed. All right, so let's kind of draw this out. You've got this slower barge going at 2.78 meters per second, faster barge going at 5.56 meters per second. And then you've got stuff going from here to here at a rate of 1,000 kilograms per minute, which, if you convert it, is about 16.7 kilograms per second. Right. And so what's happening is, they want to know how much do you have to drive this engine to keep it moving at this velocity, because as you're adding this mass is coming onto this at a speed of 2.78 meters per second. So that's kind of like the VREL, right? This is the rate, this is R, and VREL is 2.78. So how much thrust is this adding to this? How much thrust does this have to then counteract? And so really all we're doing here is T equals R times VREL. Right? How much thrust is being created by this coal that's being shoveled on? So it's 16.7 kilograms per second times 2.78 meters per second, right? Because that's the difference between those two. And you get about 46.426 newtons, right? That's how much thrust there is due to the constant shoveling of the coal. So this is how much thrust you need to counteract that to keep the barge moving at a constant velocity. And that's it for this packet. And now we're going to go back to the beginning of Chapter 9 and talk about center of mass. So, see you there. This lecture is going to be on center of mass. First of all, what is center of mass? Center of mass is the point where all the mass of an object can be considered to be concentrated. For almost all objects, center of mass and center of gravity are in the same spot. And there are multiple ways of finding the center of mass. One way is experimentally, which we're going to do on the first day. When you come in, we'll make some things and find the center of mass experimentally, but also analytically. And we can do it analytically either algebraically or with calculus. We are going to cycle back and do this later once we've got some calculus under our belts. But for now, we're going to be finding the center of mass analytically. That's when we use the math. And we're going to be doing this algebraically. And so here are the equations. Really, they're all the same equation, just applied to the different dimensions, x, y, and z. If we're dealing with a three-dimensional object, then we're going to end up with 3 coordinates for the center of mass of the object. Most of the problems we do are going to be 2-dimensional or 1-dimensional, where we're finding the center of mass. But so this is x. xcm is the x-coordinate of the center of mass. Ycm is the y-coordinate, z is the z-coordinate of the center of mass. And we calculated by taking 1 divided by capital M. Capital M is the total mass of the object. Just make sure you can see it. All right, so that's the total mass. And then what we do is we multiply this by a series of products of a piece of mass times the coordinate of that piece of mass. So really it looks like this. M1, x1 plus M2, x2, etc. Right. The idea is, right, this is the summation symbol, and I have a bunch of masses, or I have one mass that I split up into pieces. This is the mass of each piece, of each individual piece, and this is the x-coordinate of that center of mass of that individual piece, right? And this is the y-coordinate, the z-coordinate of the center of mass of each individual piece. One of the things to notice here, it's always important to pay attention to units. Let me tell you, I have survived whole parts of my physics education just paying attention to units. So let's look at the units here. 1 over m, so this is 1 over kilograms. And then this is kilograms times meters. So this ends up just being meters, which is for a location coordinate, that's exactly what we want. So let's take a look at an example now. So in our first example, we have the Sun and the Earth. We want to know where is the center of mass of this system, Earth-Sun system. So plan of action. First thing we do is draw it and then come up with a coordinate axis. So draw like an XY coordinate axis. If you have a Z, then you do a Z, but in this case it's just going to be X and Y. And really we're only going to need to do this for one dimension. So step one, coordinate axis in a drawing. 2, locate the center of mass of each body in the system. So where's the center of mass of the Sun? Where's the center of mass of the Earth? It's just going to be at the center of each sphere or circle is the way we draw it. Then we're going to calculate the center of mass for each coordinate, right? Calculate center of mass in the Y, calculate the center of mass in the X, and then finally just state the center of mass. This is the coordinate, these are the coordinates of the center of mass of the system. All right, so let's take a look now. For this system, what I'm going to do is put the center of mass at the Sun. We usually want to choose where we put the origin kind of strategically. If we can put it at the center of mass of one of the objects, that really helps because then that center of mass is going to cancel out. It's going to be 0 in our equation. And so this is, what are the coordinates here? 0, 0, right? And then this is going to be 1.5 times 10 to the 11th, 0, 0. Those are X, Y, Z coordinates for the Earth's center of mass with respect to the center of the Sun. Okay, now what? Well, we take this and we just fill it in now. So X center of mass is going to be 1 over m. And what's the total mass in this case? The total mass is going to be the mass of the Sun. Let's just say 1.996 times 10 to the 24th, or 10 to the 30th, sorry, plus 5.96 times 10 to the 24th kilograms times, right, so this is the total mass. Notice, by the way, this is pretty much inconsequential. This is practically nothing compared to this, so we don't even, if we were to add these together, this wouldn't even show up on the significant figures. But, so now I put in here the mass of the Sun times the x coordinate of the Sun. So this is 1.996 times 10 to the 30th times 0. Right, so this is nice because that's 0. It's nice that we put that axis. If we had put the axis somewhere else, that wouldn't have been 0. We wouldn't have that term just disappearing. Okay, and so now, plus, now we put in the next one, right, which would be Earth in this case. And so the Earth's mass is 5.96 times 10 to the 24th times 1.5 times 10 to the 11th meters. Right, so the Earth's mass times its coordinate, and so this ends up being 4.5 times 10 to the 5th meters. This is the center of mass of the Earth-Sun system. And notice, this is actually interesting, that this distance is less than the radius of the Sun. So the center of mass of this whole thing is actually still within the Sun. And so if we just had the Earth and the Sun revolving around each other, they would actually be revolving around some common center of mass that's just near the Sun. The Sun would actually be wobbling a little bit. And this, by the way, is how exoplanets are discovered. Planets going around other stars are discovered because they look at the Sun, the star of that system. And when they see that star wobbling a little bit, they're able to calculate the mass of the other planet and how far away it is. That's one of the ways that they find planets going around other stars. Anyway, side note. So what if? This was a simple example because we've got two spherical objects. That's it. We put the origin at one of the centers. So what if we have a system of uniform, regularly shaped solid bodies? When we say uniform, we mean uniform density, right? It's the same amount of mass per area or per volume. And if that's the case, then we can do it algebraically, like this. What if it's uniform, but the things are irregularly shaped? There, you can do it experimentally, first of all, or you can do it using calculus. You'd have to use calculus somehow. If they're non-uniform, so we have a changing density throughout, a solid or something like that, then you'd also have to use calculus. What if it has holes in it? If it has a hole, we can actually treat that as negative mass. What we do is we take the mass of the whole thing, subtract the mass of that one hole and find it that way. That's going to be example 3. But for now, we're going to do example 2. In example 2, we have a plate that's shaped with these kind of rectangles and stuff. And notice here that we're not given the mass of the body. In fact, we're not given any units at all. All we see is these squares kind of stacked up. However, since it's uniform, mass is directly proportional to area. So each area has the same mass. And so we're just going to substitute area for mass. Right? And so now you've got to break it up into a system of manageable parts. And you can do this any way you want, but there is a way that I'm going to do here, so you can try it on your own and then continue watching, or you can just follow along with what I'm going to do here, and then we'll see how it goes. All right, so here's our object, and here is that little chart that we've got off to the side. If I count the number of unit areas, what I end up with here is 20 square units, whatever the distance units are. For B, so B is this second one, A, B, C. Again, you could split it up differently, but this is how I did it. For part B, section B, it's 15 square units. That's a U, sorry. And then C comes out to 40 square units. So that gives us a total mass of, but mass again in terms of area, just 75 square units. Now we want to find the x-coordinate and y-coordinate of the center of mass of each plate. Right? So the center of mass of this plate, notice this is 2 units wide, so obviously the center is going to be right here in the middle with an x-coordinate of 1. Right? And then it's 10 tall, and so that means it's going to be right in the middle here at 5. It's going to have a y-coordinate of 5 units. Right? For B, let's see, B is 3 wide, right? It means the center of mass is going to be 1.5 units in, but I'm adding it to this, right? If this is my origin, I've got to have the same origin for all of these. So it has an x-coordinate. The center of mass has an x-coordinate of 3.5. This is 5 tall, and so that means the center is going to be 2.5 for its y-coordinate. And then for part C, the x-coordinate turns out to be 7.5 units. All right, just take the center of this thing. That's 7.5 units from the origin. And the y-coordinate is 4. Okay, so now let's take a look at, x center of mass and y center of mass. So here's the x center of mass equation. 1 over the total mass times then the mass of A times the x-coordinate of A's center, so 20 times 1 plus, and then 15 times 3.5 plus, now I'm going to do 15 times 2.5. Sorry, this should be, that's not the case. 40 times 7.5, this is for part C. And that comes out to about 4.97 units. The y center of mass, again 1 over 75. The y-coordinate of part A is 5, so 20 times 5, plus 15 times 2.5, plus 40 times 4. This comes out to 3.97. So the center of mass is 4.97, 3.97. Okay, in example 3, we have a circle and we have a hole cut out. That is supposed to be a circular hole, but I'm not a great artist, and I was trying to get the proportions right. Anyway, this hole is, the center of the hole is 0.3 meters from the center of the circle, and the hole itself has a radius of 0.4 meters, so that's what it looks like. Okay, so what is the total mass of this thing, right? Big M, again, we're not given the mass. So what we can do is we can do this in terms of area, right? The surface area. We're told it's uniform, so it has the same amount of mass for each, right, individual piece. And so the total mass is going to be the area of the big sphere. What I can do is I'll call this pi big R squared. I'll say that R, big R, is 1 meter, and little r is 0.4 meters. How about that? So the total mass is that thing, but minus the mass of this hole. And that is given by pi times little r squared. All right. And so when I write my equation here, what I'll do is I'll make the coordinate axis right here. So the center is the center of the big circle. So the x center of mass is going to be 1 over, it's going to be pi big R squared minus little r squared. Okay. And then I'm just plugging in these distances, right? So this mass is pi big R squared times 0. And now minus, I'm going to subtract, let me put it down here, minus the mass that's missing from this hole. So that's going to be pi little r squared times, and what is the center of that hole? That's 0.3 meters. All right. So now when I put all this into my calculator, we can simplify this a little bit, right? So let's see what happens. This goes away. So this is going to end up being negative. The pi's cancel out, and I'm left with r squared times 0.3 over big R squared minus little r squared, where little r is 0.4, big R is 1. And so you put that into your calculator, and you should get about negative 0.057 meters. What does that mean? That means the center of mass is actually over here, 0.057, so not too far over. But that makes a lot of sense, right? If this thing is balanced and there's no hole, that means it's the same on both sides. But if I take away something where most of the mass is concentrated on the right, that means the center of mass is going to be a little bit to the left. And so that's it for lesson 1. And I look forward to seeing you on day 1 of school. Okay, now we're back to looking at center of mass again. The reason center of mass is included in this unit is that it's really the exact same thing as conservation of momentum. Conservation of momentum, center of mass, Newton's third law are really all different ways of looking at and analyzing the same concept. Earlier in the year, we looked at center of mass this way, that the position was 1 over the total mass times the sum of the product of the individual pieces of the mass, and we add up. Now we have a new way, though, of adding up little pieces, right? For this we had to use regular shapes, things like squares, rectangles, triangles. But what if we have irregular shaped objects, or a changing distribution of mass, where something doesn't have a constant density throughout? In that case, we need calculus. So we imagine that this is getting like closer and closer to 0. And what we end up with now, our new formulas, look something like this. All right, so we're multiplying the position by that tiny little piece of mass. Right? It's still a multiplication since we're multiplying, we're adding things up. That's what the integral is about. And so then for y, works the same way. The y coordinate of the center of mass, we get this way. Okay. And we're going to end up with mass densities, different types of mass density. Things like linear mass density, surface mass density, and volume mass density. We're going to see this again later when it comes to charge, because we're going to have a certain amount of charge per area, a certain amount of charge per volume, and that kind of thing. So when you see these symbols, mass, lambda, all these things, lambda is the mass per length, and that is dm dx. Okay, so we're looking at how much mass there is in the length of the whole thing, and what that is in terms of calculus is dm dx. Okay, and then sigma is going to then be mass per area, so that's dm dA. Right? So what are we looking at? This is really, right, mass per length. This is mass per area. So this is going to have units of kilograms per meter. This is going to be kilograms per meter squared. And then rho is volume mass density. So it's dm dv. So this is mass per volume. This is kilograms per meter cubed. What this allows us to do is, if we know the total mass and the total volume, we can put these in here. But if we have a function, some function where the radius is changing, then we can use that function to find what that is as well. And then we can add it all up to get the total mass or to get rho, things like that. So we may have functions for rho. Right? The volume is actually changing as we go outward, or something like that. Okay, so here we have a derivation, one of these derivations. Here we're going to prove that the center of mass lies in the center of a uniform rod. So first we're just working with a uniform, a rod of uniform mass density. Since we're dealing with a rod, we're going to be using the linear mass density formula. So we have linear mass density is big M over L, and that's equal to dm over dx. All right. Now, if I solve this, I end up with the mass equals lambda times L. Okay. And then also, because each piece of the mass and the length, I have the same amount of mass per length each time, then I know that dm is equal to lambda dx. So now I have these two equations. If I want the center of mass, then I get that by taking 1 over big M times the integral of x dm. Right, this is our formula. Okay, and what we're going to do then is take here, instead of dm, I know dm is equal to this, lambda dx, so xcm is 1 over m x times lambda dx, right? dm is equal to this, so that's what goes in there. So this becomes now lambda over m. Lambda is some constant number, and this is x dx. Right, and where we're going from 0 to L, whatever that length is that we have. All right, so let's come up here now, take the integral. So we have, that's not x, that's supposed to be lambda. Lambda over big M, 1/2 x squared from 0 to L. So this ends up being lambda L squared over 2m. Right. But I know that lambda is m over L, right? So from here, right, lambda is m over L. So I've got m over L times L squared over 2m. M's cancel out, one of these cancels out, and I get L over 2. That's the location of the center of mass for a uniform rod. It's just right in the middle. Right, but now let's do this a little differently. Now we want to say that there's some constant. That lambda is not just, lambda is not, that we have a function for lambda, okay? Where lambda is equal to alpha x, where alpha is some constant. So again, we have this, that lambda is m over L, all these things. We know that lambda is also equal to alpha x, and I know that m is still equal to lambda L, and I know that dx is equal to lambda dm. Okay, and yeah, so let's go with that for now. So now we've got 1 over x center of mass. It's going to be 1 over big M, integrate from 0 to L of x dm. Okay, but again, dm, this is not in terms of m, so I'm not going to take the antiderivative of that. So now I come back here, 0 to L, x, and instead of dm, I can, whoops, I messed this up. Sorry, dm is equal to lambda dx. So this is going to be x times lambda dx But now lambda is not constant. In the previous problem, lambda was the same amount of mass per each part of the rod. But now I have a function for lambda. It's alpha x. So I've got 1 over the mass from 0 to L, x times alpha x dx. Right? So simplify, alpha is a constant, so I bring that out. Alpha over m from 0 to L of x squared dx. All right, notice before we had an x in here, so you might notice a little pattern. This is going to be alpha over m, 1/3 x cubed from 0 to L. And then come up here. So I get alpha over m. This is going to be L cubed over 3. Okay. Now we want to plug in. M. We need to find out what the total mass is. All right. So how do we get that? M is equal to adding up all the tiny little masses. Right. So M is going to be from 0 to L. dm is this thing, lambda dx. But lambda dx is lambda is alpha x, so alpha x dx. So I end up with, oops, don't need that, just alpha L squared over 2. And then I can plug this in here, because this is what big M is equal to. That's the total mass. All right, so a lot of substituting here. So I have alpha L cubed over 3 divided by M, which is alpha L squared over 2. Alphas cancel out. Some of the L's cancel out. And I'm left with 2L over 3. All right, that's the location of the center of mass, the x coordinate. All right. Notice before it was 1/2 L. Now it's 2L over 3. If you repeat this, and let's say that instead of this being alpha x, let's say it's alpha x cubed. Right. So before it was just constant. Right. Here x, this has an exponent of 1. We end up with 2L over 3. But watch what happens if I change this. I'm going to change this to cubed, alpha x cubed. So what happens is this is alpha x cubed. So this is then x to the 4th, right? Now this is to the 4th, or sorry, 3rd, right, 4th. So this is going to be to the 5th. Right. So let's redo that. We'll get a new thing down here. So this is going to end up being L to the 5th over 5. When I plug this in, if this is to the 3rd, right, then I'm going to end up with alpha over 3 L cubed. Right. Or L to the 4th, sorry. Alpha over 4 L to the 4th. I plug this in, and I get alpha L to the 5th over 5 over M here. This is alpha over 4 L to the 4th. Alphas cancel out. This cancels out with these, and I'm left with 4L over 5, right? So first it was 1/2 L, then it was 2L over 3. Now, right, I skipped an exponent. I skipped x squared, so this is x cubed. Notice now it's 4L over 5. So there's a little bit of a pattern here that you can see. Okay. And then this is an application of surface area mass density. Right? So here we have this triangle, and we're trying to find the x and y locations of the center of mass. It's an area, so we've got 2 dimensions to this thing. Let's take a look. And so what we've got here for the entire sigma, for the whole thing, mass per area, total mass per total area. And what's the area? It's 1/2 base times height, right? So it's 1/2 A times B as we have it in this diagram. So 1/2 AB. Okay, and that simplifies to 2M over AB. All right, but for a piece of it, then sigma is equal to dm dA. Right, and what is the area here? So it's dm, and I've got this split up. I'm taking tiny little pieces of the vertical part, right? So it's y times dx. It's the height of each little rectangle times its width, and its width is a little piece of dx. All right, so here, dm is equal to sigma y dx. Okay, and sigma for the whole thing is this, so this is equal to 2m over ab y dx. All right. Y is a function of x, though. It's linear, right? And so we can find y in terms of x, and we can use similar triangles, right? For any triangle here, we have this is A and this is B, and that's proportional to x and y. So y is equal to, so we'd have like y over x is equal to b over a. So xb, or b over a times x, right? So then I plug that into here, and I get 2m over ab times b over a x dx. Simplify further, we get 2m, the b's cancel out, and I'm left with a squared on the bottom, a squared x dx. Okay. So now I get to put all this into the function and find out. So the x, center of mass, 1 over m, and then adding up x dm. But dm is this whole thing, right? So this is 1 over m from 0 to a. I'm going from here all the way for the full length of the triangle. X times 2m over a squared x dx. Okay, so let's get out everything that we can get out here. The m cancels out with the m. I'm left with 2 over a squared, and then in the integral, x squared dx. All right, so 2 over a squared, x cubed over 3 from 0 to a. So that's going to be 2 over a squared, and then a cubed over 3. So I end up with 2/3 of a. And that makes sense, that this is going to be 2/3 of the way down this line. Right? Now that's the x part of the center of mass. Finding the y part of the center of mass is here for you. All right? But the idea is that generally it's going to be 1/3 of the way from the edge of the heavy side, right? So this is 1/3 of the way this way, and then this is going to be 1/3 this way. It's going to end up being 1/3 of b. Okay? And so for a system of particles, let's see what we have here. Looking at the next thing, Newton's second law for a system of particles of total mass m. This works, Newton's second law works also for a whole system of particles. So here we have, right, this is what we're doing now. This is finding the common center of mass, right, the common location. This is finding the velocity, overall velocity. And here this also works for Newton's second law, ma, right? But if I add up ma of each of the particles, then what I'll end up with, adding them all up, is just the net force. Okay, and so that's why we call this is Newton's second law for a system of particles. And so there in that other box on this page, right there, we fill this in. Ma for center of mass is F1 plus F2 plus F3, right, etc. So then A of the center of mass, the acceleration of the center of mass, is 1 over the total mass times the sum of all the forces. And so here we see what we had been using before, that instead of having to take every individual object and analyze all the forces on them and then substitute all the equations, we would look at all of the objects that are part of the system, and if they had a common acceleration, then we could just look at all the external forces and see how they add up. Right. Okay, so here's an example of this. You've got three particles that are initially at rest, acted on by external forces as shown in the diagram. Calculate the acceleration of the center of mass of the three-particle system. So all we have to do here is take the 1 over the total mass. And what is the total mass in this case? It's 16 kilograms. And multiply it by all these forces. Now the forces end up being 6 newtons at 180 degrees. So that is, let's say, negative 6I. And then 12 newtons at 45 degrees. So that's going to be 12 times root 2 over 2 I plus 12 root 2 over 2 J. And then 14 newtons at 0 degrees. So this is going to be plus 14 newtons in the I direction. And then, let's see, this will all just kind of add up here. So negative 6 plus 14 is 8. So we've got 8I plus 12 root 2 over 2I. Being lazy and not feeling like doing the calculations here, over 16 kilograms. And the units up here are newtons. And so that's it, whatever that adds up to. And we'll just leave it in that form of unit vector notation. Makes it easier that way. Okay, so in this explosion of a projectile thing, it goes up into the air and it explodes, but it explodes so that mass m falls straight down, and then mass 2m continues on. And what that does is it allows that other mass to go farther than it would have otherwise. So the first thing we do is we use the range formula to find out where the center of mass lands. All right, so R equals v squared sine of 20 over v squared sine of 2 theta over g. So that's, we plug our numbers in. V is 10, so 10 sine of 2 theta, so theta in this case is 60, so it's going to be 120 over g. These cancel out. So sine of, this is squared, so I'm left with a 10. This is root 3 over 2, so I end up with 10 root 3 over 2, so let's say 5 root 3. Okay, which is about 8.7 meters. Now, here's my diagram. So here, this full range, all right, and then if I divide that in half, this is 4.35 meters from here to here. Okay. And then what I can do is I can calculate, if this is the center of mass and one object of mass m is here, then I can figure out where on the other side the other piece is, because the center of mass is going to be conserved. So if this is where the center of mass is, I know, so looking at the equation this way, right? X center of mass is 1 over big M, and then adding up each of these locations, right? Mi x1 plus m2 x2, and that's it. There are only two pieces to this. I know this is 3m, and I know that this, let's take this to be that piece. This is just the m, and somewhere over here is going to be 2m. And if I take this as my origin, then or let's see, what did I decide to do here? Be easier if I just do, oh, okay, so if I take this as the origin, right here, that makes that piece go away. So 1 kilogram times 0 meters, that's easy. And now 2m, so that's 2m times x2. I don't know what that is, but I do know that the center of mass is 4.35. Right. So we're going to be taking 2/3, or 4.35 times 3 divided by 2. So when we solve for x2 this way, we end up with 6.525. That means it's 6.525 from here. So then I add that to this, and that'll give me where it lands from the place it was initially shot. Right. So this 4.35 plus 6.525 comes out to about 10 point something meters or so. Okay. And last example. So we have a man, mass m, suspended from a rope attached to a hot air balloon of mass 2m. If the man climbs up the rope at speed v, what is the velocity of the balloon? Right. So we assume that the balloon is there and the man is there, and relative to the ground, it's not moving. But then the man starts to climb up. Okay. So we got to see what is the velocity of the balloon. And here we can use just conservation of momentum. Right. Initially the momentum is 0, and then we've got the balloon and the man. So here the total momentum has to equal 0, but the man has a momentum upwards of mv. And we know the balloon has mass 2m. So that means his upward momentum has to be the same as the downward momentum of the balloon. Right. But if the balloon has mass 2m, then the balloon has to have a velocity of 1/2 in order for the total velocity, the total momentum, to remain 0. Okay. And that's it for this unit.